Chemical reactions!
That was not planned. Actually, that wasn't. That's just how nerdy we are. Alright, guys, what's a chemical reaction?
A chemical reaction is when atoms are rearranged to form a new substance. Okay?
Rearrangement's kind of important. What it means, essentially, if you have played with Lego, you understand chemical reactions. Take things apart, put them together in a new way, ta-da, reaction.
The general form of a chemical reaction is reactants are always on the left side. Okay? Products are always on the right, and there's an arrow in the middle that represents the changing process. Okay, so we see a nice pretty example here. Reactants on the left, products on the right, and a beautiful arrow in the middle to represent the change.
And if that required the explanation that Mr. Regnier just gave it, talk to us. You might need some help. Because it says reactants, products, and the arrow. But guys, as much as we can make fun of it, when we ask you what are the reactants in a reaction, you better be looking at the left side. Now, evidence. How do you know if a chemical reaction has taken place? Well, there's two sides to this. There's theoretical knowledge and there's empirical knowledge. Theoretical knowledge is stuff that you theorize is happening. It's not something that you actually have seen, touched, tasted, felt. It's just stuff that you assume to understand. Most of your knowledge that you have is actually theoretical. Most of you know that falling off a very tall building would hurt. But that is theoretical because most of you have not yet jumped off tall buildings. Yet. Who knows? There might come a day when, you frustrate us, we take you up to the roof, and we conduct an experiment. We're pretty sure you're going to hit the grass. It'll be nice and soft. Now, the theoretical is that a new substance has formed. The empirical is what we actually see. We actually see color change. We actually see odor. Is this starting to sound like junior high? It should. You guys know this.
So reaction can be expressed in several ways. Number one, word equations, which is like a full sentence, and in chemical equations. Okay, word equations use chemical names, and you need to find key words to determine if a species is a reactant or a product. Things like so-and-so produces this, okay, or reacts with this to produce this. Okay, these keywords tell you which ones are reactants or which ones are products. And we'll get to these a little bit later on when we look at more examples. Okay, the chemical equation on the other hand, uses chemical symbols. Okay, the arrow will determine the size for the reactants and the products. So the chemical symbols, what we're talking about, okay, is not just the chemical name. You're incorporating the symbols off the periodic table like we mentioned in naming.
Now, better than just saying that's what it is, let's actually take a look at this one. We have an example of a word equation. Hydrogen gas and oxygen gas react to form water vapor. So, right now, these are our key words. React to form. Form means that we're going to make our products. React to kind of implies that right now we have reactants. So that's the point where the arrow shows up. Now, the only real tricky thing out of this, guys, is if you were trying to take this up here, most of you could look at H2 and say that is hydrogen gas. Please don't ever say that is dihydrogen gas. The actual tricky part is, what if we gave you the names and we expected you to write the formula? Guys, all of our naming rules apply. So when it says oxygen gas, you better know that we are talking about about O2. Sorry, I was reading ahead. Naming also applies to water. Most of you know that's H2O, but vapor. Gas. If it was at room temperature, you should say that water is, I don't know,
solid.
Liquid. We should say that water is a liquid. However, because it says vapor, it better say H2O is a gas.
And guys, also with the chemical equation, make sure that you are incorporating these when you're writing your final statement, just like Mr. McLeod kind of led to, but not really.
Oh, and there's one more keyword. Most of you already know the keyword and. It kind of means this plus this. Oh, well, that's exactly what it looks like in the formula.
Woo! So when we look at reactions overall, there's 5 basic reaction types. Okay, formation, decomposition, single replacement, double replacement, and combustion.
Actually, it's not DDR. Sorry. I would just rather be playing video games right now. It's just a DR. Now, the combustion one leads us to, guys, to an important demo that we need to do. So here it goes.
Whoa, nice fire, Mr. McLeod.
That is an absolute great demo. The time and effort that went into looking up this YouTube video to show you what a combustion reaction looks like shows that we are truly teachers that care. Alright, now guys, the combustion ones that we look at, yeah, burn baby burn. Burn is actually a very good keyword for those reaction types. Or if it says like, your couch is set on fire, what's the chemical reaction? Well, that's going to be a combustion. Now, for all these formation types, we're going to go through all 5 of them. They're all going to look very similar. Now, there's going to be this little bit to help you out. Elements come together to form a compound. Now, the key word is in big capital letters there, forming the compound. Now, when we look at this, underneath, elements are also made of atoms. Compounds are made of molecules. So we're trying to use chemical language. So when we talk to you in class, you can understand the language that we are using as well. Most textbooks will list this general form. X plus Y makes XY. This looks like something inappropriate that happens, and that's how babies are made. The general form that might make your life a little bit easier is to use letters E and C, because E represents an element and C represents a compound. When you look at an example, you should start trying to figure out, is what I'm looking at an element or a compound? This will lead you to the reaction type. Let's hit the first example.
All right, the first example we look at is sodium and chlorine coming together to make sodium chloride, okay, which is this example right here. Okay, we see sodium, okay, this is an element, okay, it comes right off of the periodic table, okay,
So we'll put an E.
okay, we look at chlorine, comes right off the periodic table, element, and they come together to form a compound, which is NaCl, okay, and again, everything balances out. We don't actually see them balance out quite yet. That's something we're going to lead on to the next slide.
Next example, you can see very similar. You have Fe, which is ferrous on your periodic table, or ferric. You guys know it better as iron. Iron is an element because it's on that table. You also have oxygen, O2, so that is an element. Now at this point, guys, I have enough information knowing that on one side of the arrow, all I have are E's. That's actually a clue. If all I have are E's, this must be a formation reaction. Or if all I have is the product. If the only thing I know is that I make one single compound, that is a clue that I have a formation.
Perfect. And again, we end up seeing the same kind of thing with the last example. Now this looks different than the first two because we have several reactants here. But as you notice, each one of the reactants we see here are all elements. Okay, and they are all coming together to form how many products? One giant compound. So again, we can still classify this as a formation because we have all elements coming together to form a compound.
Now, similar to what this sounds like, formation, it kind of sounds like you're going to build something. A decomposition is the opposite, and we will see that in our general formula types. This is the exact same thing that we saw in the last one. This little XY relationship here is going through a breakup. X and Y are going to go their own separate ways. Or, if we were to look at it with more appropriate letters, we have a single compound as a reactant. That single compound will form elemental products. And the reason that I would say elemental products, or elements, is that you will make exactly how many you need. It's not always 2. If the compound had 4 elements, you would have 4 products. Example time.
Perfect. So now, again, we're going to break this up like we saw before. Okay, we draw our line. The common indicators, like Mr. McLeod said, is we have one compound as our reactants. We see here we have one compound. Now, that's enough for us to say, hey, this is a decomposition reaction. But if you want to be thorough, okay, we end up taking a look. We end up seeing our CO2 breaking up into both carbon and oxygen, which are both elements right off of the periodic table. Okay, so again, all of this leads together, follows this format, and we would call it our decomposition.
As we go down to the next one, this is just another reverse of the water. We're actually going to do this do this demo in one of our labs. This is a very common one where we take water, which is a compound. At this point, we're pretty sure this is a decomposition, but we'll double check. We have 2 elements as products. This is a decomposition.
Last but not least, again, we have one compound breaking up into its element. But now, what we see with this compound is we see 3 different elements. So what we should see are 3 different products. And that's exactly what we see here. Now, one thing you may be looking at is like, why is there 1 S on the left side and 8 on the right? But that is something for future videos. So just hang on to that question. We'll get there.
Well, you should still have it from your naming. Guys, when sulfur is all by himself, he's S8. When he's in a compound, he can be somebody else. We'll deal with the fact that there's only 1 and 8 later, but you should still know this guy had to be 8. Now, I want to give you guys one very common trick question. If we have a compound, or a reaction formula that says H2CO3 becomes H2O, liquid, sorry, that's a really sloppy L, and a CO2 gas, is this a decomposition? Well, many students will start looking at this, they'll draw their line, they'll look at the reactant, it's a compound, they will say that this is a decomposition. However, if we go look at the products, H2O is a compound. CO2 is a compound. Now, while this is a type of decomposition, this is not the type of decomposition that you, as grade 10 students in Alberta, are going to recognize as decomposition. You would say that this is just going to be a reaction type classified as other.
Okay, next up is the single replacement reaction. Okay, again, we see the general form right here. Okay. Now, what's different about this one is we see both compounds and elements on both sides of our arrow in both the reactants and the products. A nice way of trying to think about this is we have a couple right here. Okay, and what we end up seeing here is we see a change of partners. Okay, we end up seeing B and C rotate spots, so they form a new couple and leaving poor A out of the circle. Okay, so again, however you want to think about it, it's completely up to you. But let's take a look at some examples.
Okay, guys, so this first example, we have HCl, which is hydrochloric acid, practice your naming, plus zinc. Now, at the moment, I look at HCl and I see a compound. I look at zinc and I see an element. If I have a compound and an element, well, that means the element is going to come in and do a singular replacement of one element in my compound. This zinc is going to come in and he's going to take either the H or the Cl's spot. Looking at the products, we see that he bonded with the Cl. So this is now a compound, and this is my new element. If I know that I need to classify this, or if I know that I am trying to figure out how to classify this, I would look at compound, element, compound, element. Oh, well, that looks like somebody's been replaced. But only one thing has been replaced, so it would be a single replacement.
All right, now we're going to take a look at the second one real quick. Again, we end up seeing a compound, element. Okay, now what we're going to see a singular replacement. F is going to go into here and exchange places with one of these guys. Whoa, I don't know why that just turned red. Okay, but we end up seeing it switch places, and we know which one it exchanges due to our products. And now what we end up seeing is the compound, an element again, and we see the compound, element, and we are classifying this as a single replacement.
All right, so what would be more complicated than replacing one thing?
Huh, replacing 2 things!
Double replacements! 2 compounds will react to form new compounds. Now this just looks like a mathematical fun formula. C plus C equals C plus C. Give that to your math teacher, it'll drive them nuts. How we actually use that in chemistry, guys, is that when you have 2 compounds reacting and you form 2 new compounds, we're going to call that a double replacement. In this, there's still some replacement procedures going on that we'll talk about in a little bit, but if we were to look at this really quickly, if I see that there is more than one capital letter, this must be a compound. I see more than one capital letter, this is a compound. I see more than one capital letter, this is a compound. I see more than one capital letter, this is a compound. This is 2 compounds becoming 2 compounds, that's a double replacement.
Woo! Okay, so let's take a look at the third one. Okay, we're going to skip over the second one. It's kind of similar. But what you should notice here is we have a special kind of reaction happening here. Okay, obviously we see more than one capital letter. We see compound, a compound, compound, and a compound. Okay, so again, we can classify this as a double replacement, but this is a special double replacement reaction because we end up seeing our wonderful H friend here in aqueous, which makes this a
Base.
no acid.
Ah.
And we also see that we have OH in the aqueous, which makes it a
Base.
perfect. Good job, McLeod.
If you keep saying base, you'll be right half the time.
So if we have an acid and a base reacting together, we end up seeing a neutralization reaction, which falls into the category of a double replacement.
Now, just because Mr. Regnier's gets to be a double replacement with a neutralization, we should be able to see right here we have water. That makes this guy the salt. You don't need to know that for now, but it's good to be able to recognize it. I'd also like to point out this guy was a special reaction too. We had aqueous, aqueous, aqueous. One guy is a solid. If we mix a whole bunch
What's
of
the name for that again?
aqueous things and we make a solid, how would we figure out it was a solid? We'd have to use some sort of table. A table that would tell us what an ionic compound does in water.
Solubility table.
In this case, the calcium carbonate was actually a precipitate. Everybody's favorite,
Combustion!
fire. Now, first thing I want you to do, I want you to ignore all of the X's and the Y's. You know what? You can ignore the Z for now, too. Guys, this is going to come up when we start working with our balancing. Essentially, here is your combustions. A hydrocarbon. Hydro sounds like hydrogen. Carbon sounds like C's. So you have H's and C's. Well, that's exactly what's right here. Any hydrocarbon will react with... I'm not sure what's moving here. Any hydrocarbon will react with oxygen to burn. And they will always make the exact same thing. They will always make carbon dioxide as a gas and water vapor as a gas. But, teachers, you told me H2O is a liquid. Well, guys, you may or may not know this. I'm sorry to let the cat out of the bag. Fire is hot. If fire is hot, water will not be a liquid. It will evaporate and be a gas. Now,
So to start going through the examples as we have down here, okay, all we're looking for here is the fact that we're dealing with a hydrocarbon and we're dealing with oxygen, which we see here. It doesn't matter at this point with the 3 and the 8 because we see that it's a hydrocarbon. We see that it's reacting with oxygen. It's always going to produce carbon dioxide and water.
The products here are really boring, aren't they, guys? They're all the same. But that's a good thing. As soon as you see H and C react with O, all the products are the same. Make your life easy.
Done.
Word equations. Now, word equations, they one up your game a little bit. You got to know what you're doing. We've told you what these reaction types are. So that would be a good clue. But if I look at this, I've got my carbon. I'm going to say that that's a solid because I'm a good chemist and I'm not skipping states. Next, I'm going to have oxygen. Most of you are going to write O. The good chemists are going to write O2, and they're going to put that it's a gas. This is going to react to form carbon dioxide. And carbon dioxide is one of the few molecular compounds you must know. You must know it's a gas.
Okay, now if we take a look at this decomposition example, okay, we have the fact that it is water. We all know the wonderful chemical equation for water is H2O. Okay, now what we're going to end up seeing is we're going to see this in the liquid phase. Okay, now it's going to break down into its elements. Now this
but Mr. Regnier, it didn't tell you what the elements are.
Oh no! Oh, what are we going to do? We just have to look at what's in the compound. We obviously know that it's hydrogen and oxygen, so we break it down into those separate elements. Now, what you should remember is the diatomic molecules or diatomic elements from the periodic table that we discussed earlier. So when we write H, it's always H2. Gas plus O2 gas. And you are off to the races.
Hey guys, how do you know how many elements exist or how do you know how to break it down? Remember, you're just looking for capital letters. Easy. Now, single replacements. Single replacement, magnesium is placed into a hydrochloric acid forming magnesium chloride hydrogen gas. All right, so we started out really quick. Magnesium is a solid plus hydrochloric acid. This is going to give me, and this is the forming part coming in from my arrow, this is going to give me magnesium chloride. I'm going to go MgCl. I'm going to get my periodic table. Because I am making products, I need to check charges. This is MgCl2, and I don't know his state yet, plus a hydrogen gas. Now, the reason that I'm saying I don't know his state yet is I have an ionic compound. I need to ask myself in this reaction, is water present? Water is present when it says aqueous, or it says solutions, or when it says acid. So water is present. I go to my table, I go to the column for chlorine, I find magnesium. Magnesium is in the most category. The most category is AQ.
Perfect. Okay, let's look at something a little harder. Okay, obviously we have liquid bromine dropped on a solid piece of sodium iodide. So let's break this down. Initially, we have liquid bromine. Okay, this is just again, another diatomic. Okay, and we end up seeing this in the liquid phase according to our periodic table. Now we are adding it to a piece of sodium iodide, NaI. Okay, obviously this is a solid because it says a solid piece right here. Okay, but what's different about this question is the fact that we are not given any products. Okay, so we have to try to predict what the products are going to be. Now we know that this is, again, an element and a compound, so we know it's a single replacement, as it says up here as well. Okay, so we know bromine is going to go in and replace one of these guys. Now, we know sodium has a plus charge. Iodide has a minus charge.
What would bromine like to do? If bromine is going to join these, he can do whatever he wants. So we go to the table and bromine should be
negative.
So, who's he going to replace?
He has to replace the negative. He has to replace the iodide, strictly because you always have opposite charges that attract one another. Okay, so what we end up seeing is we see a new product form over here of NaBr. Okay, we don't know what the state is quite yet. Okay, plus, now we have iodide kicked out by itself.
How did you know that was a solid, Mr. Regnier? Did you memorize that?
Yes.
The other clue would be, guys, if you don't know, you should know it's I2, but if you don't know the state, check the table. Now, Regnier still has one job left. He's got this really tricky one right here. How do we figure out this thing's state? Guys, you don't even need that periodic table that he's waving. Is there water in this question? Liquid does not mean water.
Solid. Done and done.
Double replacements. Okay. These ones become fun.
Okay, so now we're going to take a look at a double replacement reaction. Okay, we obviously have the keywords for looking at our word equation. We have sodium hydroxide solution, okay, phosphoric acid, okay, are mixed to form, okay, sodium phosphate and water. Now, what we end up seeing is we can start with our reactants. Sodium hydroxide, okay, obviously it's in solution, so we have aqueous plus phosphoric acid, H3PO4, aqueous, arrow, mix to form our sodium, which has a +1 charge, phosphate. Why it went red, I don't know. We know phosphate has a -3, sodium has a +1, so we see Na3PO4 plus H2O. Okay? We end up seeing a liquid form, and what do we get for a state on here? We can check our wonderful solubility table, and we'd end up seeing that it's aqueous. Okay, so now we end up having all of our states, we have all of our compounds made correctly. You need to make sure when you're constructing these from the name that you are still balancing out your charges that you've seen before.
Where did that show up, Mr. Regnier? In the two things that had to be 3s. We had to because phosphate had a higher charge. Now, this last one. And guys, to be perfectly honest, predicting reactions for what the products you're going to make are is actually a very tough skill until you start to look at the reaction types. Silver nitrate. Apparently my pen is now going all over the place for color. Is mixed with potassium chloride. Solutions. But it doesn't tell me anything else. How do I figure out what my products should be? At this point, I have a compound, I have a compound. What kind of reaction is that? Let's pretend that wasn't there. If it wasn't telling you this was double replacement, compound plus compound, I need to make 2 new compounds. So, similar to single replacement, he's positive, he's negative. He's positive, he's negative. The positives always go first, the negatives always go second. What this allows for now is to do a double replacement. It seems like we're going to make 2 new compounds. how do we figure out what's going to happen? Normally, when I'm writing these guys, I'm going to build a lot more of my knowledge into it. But what we can do is just start with the first thing. The first thing's a positive. He has to mix with one of these two. He cannot mix with the positive one, so he has to mix with the Cl. This will be AgCl with an unknown state, plus, if we've just put Ag and Cl together, that means we have to take these guys and put them together, KNO3 in an unknown state. Pause the video if you need. Go check for these if you want to practice. Solid AQ. Probably went a little fast there, guys, but you should have that skill by now. Last one. Burning!
Yeah, combustion.
This is easy. All right, let's see. I'm going to start it here with methane. You guys are expected to memorize the formula for methane.
Next up, we know it reacts with oxygen. Since it is burning, we need oxygen in order to light any kind of fire. Now, Mr. McLeod,
let's see if we can do this simultaneously.
All right, here we go.
Ready?
Go.
Hey, look at that. We didn't even pick the same product. Good
Look
job,
at that.
team. All right, so, ladies and gentlemen, as you're doing this, everything is a CO2 leads to H2O. Good job, team. Those will be really easy to predict, but they're not as much fun to balance, but that's a problem for tomorrow. Last one, it's pretty much still just another combustion. This thing burns in oxygen. Try to set it up. If you have issues with it, come see us tomorrow.